I am Vsevolod Bogayenko and I would like to present you the results of the studies on computing the values of psi-Caputo fractional derivative using CUDA-10. I will start from some broader context. In significantly heterogeneous porous media, classical models of mass transport based on traditional integer order differential equations would produce adequate simulation results because of memory effects that can be observed in such media. To make adequate simulations and predictions, we need some new mathematical tools to capture these memory effects. Such tools are fractional derivatives that are the generalizations of classical derivative concepts. On this slide, you can see several variants of fractional derivatives that can be used in such models. First, it's a classical Caputo derivative with a singular kernel, that is an integral with singular kernel. The second, it's its generalization, a psi-Caputo derivative that has functional parameter. And the third one is Caputo-Catugampola derivative, where this functional parameter has a power form. So we consider a three-dimensional diffusion equation that models diffusion in porous media of fractal structure. This equation has a psi-Caputo derivative with respect to the time variable in its left part. To discretize this equation, we use the locally one-dimensional finite difference scheme that converts a three-dimensional equation into a series of one-dimensional equations. To discretize the integral differential operator, that is the fractional derivative, we use the simplest first-order scheme that results in sums with a number of terms equal to the time step number. These sums form the main part of computational complexity while solving such equations. Such computational scheme has a linear complexity, and to reduce it from linear to constant, we use the algorithm based on the series expansion of the integrals. Such algorithm is recurrent and due to this property allows reducing computational complexity. Further, we will consider both the full summation and the series expansion algorithms. How these computational schemes were implemented in parallel. For central processor, we used OpenMP as locally one-dimensional finite difference schemes has a natural parallelism. For graphical processors, we used the mapping where one grid node of three-dimensional grid is mapped onto one thread. Threads were grouped into groups of controllable size to make use of local memory in both full summation and series expansion algorithms. In both these algorithms, sums were splitted into vector operations of some controllable size dependent on what data types are present in the respective language. So we used double, float, and half precision data types and up to 16 terms vectors. Additionally, we make use of matrix multiply-add operation that is hardware implemented in the so-called tensor cores. Such operation is used in the series expansion algorithm. It produces 16 matrix vector multiplications, from which we used only one. All algorithms were implemented in both CUDA and OpenCL languages, except the situations of tensor cores usage that is accessible only from CUDA, and 8 and 16 terms vectors that can be accessed only from OpenCL. And the main goal of the study was to test the performance and accuracy of all these algorithms and their software implementations. For this purpose, we used the cluster of the Institute of Cybernetics. In the first series of computational experiments, we tested the performance of the algorithms on a grid of a fixed size. The results confirm that the full summation algorithms has a linear computational complexity, while the series expansion algorithms is of a constant complexity. While doing 200 iterations, we obtained up to 5 times speed up of the GPU algorithms comparing with CPU implementation. When a full summation algorithm was implemented in CUDA, comparing to the usage of double precision data type, float precision implementation performed up to 2 times faster, while the half precision implementation performed up to 3 times faster. No such effect was observed in the OpenCL implementation. For the series expansion algorithms, float and half only slightly changed execution time comparing to double in both CUDA and OpenCL implementation. The usage of tensor cores produced the results faster than all other algorithms. The usage of vector data types accelerated computations only for the case of single precision floating point data type in CUDA implementation, and in the case of large vector types in OpenCL, that is with 16 terms. To explain this behavior, we looked into the assembly sources generated by CUDA and OpenCL compilers. These sources were quite similar, but there were some differences that explain different performance of CUDA and OpenCL implementations. Talking about the usage of vector data types, we can state that both compilers do not generate vector arithmetic instructions, but generate vectorized memory access instructions. CUDA compiler generates additional vectorization when single precision floating point data are read from local memory, and this feature leads to its better performance when single precision floating point data type was used. Both compilers utilize this automatic loop unwinding. However, when a vector variable is accessed, fixed offsets to the corresponding memory are computed on each iteration. Thus, the increase of vector data type size leads to the decrease of the number of auxiliary operations, and it leads to the situation when OpenCL implementation performs faster than CUDA in some cases because it allows using larger vector data types. Another found aspect is that with the default settings, CUDA compiler implements division operation in a full accuracy instruction, while OpenCL compiler uses an approximated instruction. In the series expansion algorithm, which is more influenced by memory access operations, these aspects do not influence performance too much. But for the full summation algorithm, which is mostly influenced by the performance of arithmetic instructions, OpenCL code overperforms the CUDA code. In the second series of computational experiments, we studied the efficiency of GPU implementations and especially of vectorized implementation in the situation when the size of the grid changes. In general, 2 times speedup was obtained while performing the solution of the considered three-dimensional diffusion equation when on GPU we performed the computation of fractional derivative values while other operations were performed on central processor. Regardless of the used vector scalar data type, the speedup increased with the increase of grid size for the full summation algorithm and remained constant for the series expansion one. The usage of tensor cores that operates with the half precision floating point data type yields additional 12% increase of speedup compared with the usage of half data type itself without vectorization, and however it is only 2% increase of speed up comparing to the fastest case of 4 components single precision floating point vector. The last issue we studied is the influence of data type precision on the accuracy of the obtained solution. So, lowering of data type precision had a little influence on the solution accuracy when the full summation algorithm was used. So it is quite stable to the data type size, data type precision. For the series expansion algorithm, starting from some time step, the error starts to linearly increase when data types of lower precision were used. Such behavior was observed both for single precision floating point and half precision floating point, and the accuracy was close to equal with the accuracy of the full summation algorithm when double precision data type was used. Summarizing, I can say that the usage of different scalar and vector data types along with specific hardware implemented operations which are available through Q.10 framework can help speeding up the computations of psi-Caputo derivative values while solving different time fractional differential equations. The implementation of the straightforward full summation algorithm was more efficient in OpenCL due to the differences in compiling the division operation between CUDA and OpenCL compilers. This algorithm can be accelerated using lower precision data types without significant loss of accuracy. For the approximating series expansion algorithm that has lower computational complexity, the usage of CUDA is preferable and the highest precision data type should be used. The usage of tensor cores wasn't very efficient for the considered problem. However, comparing to the fastest case, an additional 2% acceleration was obtained. Thank you for your attention.